Okay, so we know that there are broadly two types of current, or two categories where you could group current into AC and DC. And AC is short for alternating current, while DC is short for direct current. And we know that the representation for AC is usually a sinusoidal graph, which is given by, what we see in the next slide. But what are the main differences apart from the way the graph looks? The first one is that for AC, alternating current, the potential difference of means electricity changes direction. So that's why you have that graph going up and down, okay, like a mountain and then a valley. And then you have another mountain again and then a valley, and so on and so forth. So it changes direction. The potential difference changes polarity. It can be positive or negative. And then what's next for alternating current is that it's usually used in the mains electricity. That's what you have, like what you have from a plug. Um, that's your electric current coming from the power station. Let me put it that way. Okay. Then for direct current, you have the potential difference across cells and batteries. It's always in the same direction. It does not change polarity. It's not positive sometimes and negative some other time. Okay. Then where would you find direct current coming from? Mostly batteries and solar cells. All of them are direct current components. Okay, so let's see the graph I was talking about. So this is the graph for direct current, the one on the left-hand side. And this is the graph for alternating current. You can see what they meant by the polarity changes. So sometimes it's positive. That's when you have the crest, what they call the crest. And then some other times it's negative, what you call the trough. Okay, so crests are the ones that look like mountains, and then troughs are the ones that look like valleys. That's for alternating current. But for direct current, it's just fixed. It's just like a straight line. You can liken it to a straight line graph that is constant in mathematics, those ones that are just something like y equals 2, just a straight line passing through the y-axis, going across the y-axis at the value 2. So that's what you can liken the DC graph to. Okay. All right, so let's see what other things that characterize alternating current. Like we said, it's main electricity. That is the mains, the one that comes from your sockets and your plugs. In the UK, the frequency is 50 hertz. The voltage is usually 230. And I think it's similar to what we have in Nigeria. It's about that voltage too. Okay, so let's see some other things that relate to electricity. The parts of your plug. Of course, typically your plug has 3 pins. Okay, 3 pins that it has out, that stick out, that enable it to be plugged into the socket on the wall. And the first one is the live wire. But the live wire is usually the one that's connected to the fuse. Okay, it carries the alternating potential difference from the supply. That's the AC current. That's why it's called the live wire. Okay, then the neutral wire completes the circuit, or in other words, that's the bit of it that balances the circuitry on the other side. Then the one that is usually optional, you notice it's usually optional. There are some plugs that that just have 2 pins. Okay, So the third pin that's optional in those plugs that have 2 pins is the earth wire. And that one is for what? It's simply a safety wire for stopping the appliance from becoming live. What that means is that, for instance, you know, electrical devices can somewhat store excess charges as they work. Okay. I don't know if you've had that experience before where you touched something that was on. It may not even be on at the time you touched it, but you just touched it and you felt like, you know, you felt a sensation in your fingers as if something, you know, you got a small shock. Okay. So it's not, the shock is not strong enough to be like electrocution, but you would feel it, you know, and well, it's not so, um, um, it's not dangerous, but at the same time, it's not what you like to be feeling all the time. Okay, so that's the earth wire helps you to get rid of those excess charges. Okay, then excess charges can also build up as, you know, when rain falls and you have lightning, and you know sometimes we forget to, you know, unplug devices from the socket, and lightning is natural electricity. Can't run away from that fact. It's natural electricity. In fact, it's safe to say that man was able to discover electricity. We didn't invent it. We simply discovered it and discovered the rules, and we harnessed those rules to create what we have today, in the world, you know, as electricity and all that. But as to whether we invented electricity, that's not true. Okay. Yes, the devices that came out from, that came to use electricity were invented, no doubt. But electricity itself is a natural phenomenon that man simply discovered and found a way to harness. So lightning is natural electricity, and it's as dangerous as electricity that's going through, what they call those high tension wires. So if somehow a house is not well earthed, okay, same earthing thing that we talk about. If a house is not well earthed, guess what can happen? Lightning can find its way into, you know, through the electrical wiring and can get to an appliance that's still connected to the socket. And well, it may not electrocute anybody, like I said, but the excess charges, it will look like as if power passed through that, device. But then, of course, the device was not on at that time, so it will just hang around it, okay? Just maybe on the surface, and charges can stay on the surface of something. As soon as your hand touches it, those charges leave the surface of that thing and attempt to pass through the human body. Okay, because of course we all know that the human body is made up of more than 80% of water, and even that water is mostly salt and, you know, and acids and all that, so many chemicals in the body, which make the body a perfect conductor of electricity. Okay, so let's not forget that fact. All right, moving on. I just felt I should just say that because of the we have this reference to this. If it's necessary, well, maybe in paper 1 or paper 2, I'm not too sure, but the idea will still count later. Okay, so let's take a look at the fuse. So we all know what the fuse is. Basically, the fuse's job is to break the circuit if the current flow is too high and will damage that device. Okay, so it's always good to go with a plug that has a working fuse. Okay, and guess what? If the fuse gets what do you call it? What do you call it? If the fuse melts as a result of the high current, that is the too much current that is about to enter the device, you know, there's always that tendency for one to try to bypass the fuse. Oh, let me make it work, let me make it work, and you try to bypass it. That would be setting up that equipment for damage. So it's always good to have a working fuse. And so the wire in a fuse is a light wire that melts easily, like you can see here. And if it's too high, you know, current usually heats up metal, right? So if it's too high, it will heat it up faster than it could take it. And then it would melt it and break the circuit. If the device works at 3 amps, a 5 amps fuse is used. If it works at 10 amps, a 13 amps fuse is used. Okay, so this is for different devices that are working at different um, current levels. So it's always good to take a look at the back of your plug to know which level the device is working at for replacing the fuse. Okay, so here we go. Sorry, let me take a look at those figures again. 3 amps, we need a 5 amp fuse. 10 amps, we need a 13 amp fuse. Okay, so just see the difference. This one is 3 amps higher than what it's supposed to use. And this one is 2 amps higher than the 3 amps that the device would use. Okay, so I think this is like a test question. The question is, okay, the colors. All right. So that would make me to go back to that diagram so that we take note of the colors. The correct answer is D. The earth wire is green and yellow, okay, while the live wire is brown and the neutral wire is blue. Okay, so if you look at the diagram, everything matches what we see. Now, I'm sure I don't know if you've opened up some plugs. They don't really follow this convention all the time. But let's just pretend we're in a perfect world and everything goes with the flow. So yeah. All right, so remember the colors, green and yellow, earth, brown is for live, and blue is for neutral. Okay, so moving on. Electrical power, I told you what power is. Product of what current and potential difference, IV or VI, anyone. It's multiplication, and multiplication can be, you can switch sides. It's there's a word for it. I've forgotten that word. It's I've forgotten. Anyway, you know what I'm talking about, right? 3 times 5 and 5 times 3 are the same. So multiplication can be switched, okay? Just like addition. Yeah. Did you say something?
No.
Okay. All right. So there's this not really a definition for power, but it's related to the potential difference across the device and the current that is passing through it by that equation. So if they ask you, for instance, in this question, you are asked to find the power, ensure that the units are tight, amperes for current and volts for potential difference. And when you simply multiply both of them, your answer will be in watts or watts, okay? And of course, this is another example, but we're moving on. Okay, so I think we've made a subtle reference to the national grid, a system of cables and transformers. Of course, there are other devices. This is the simplest definition of what the national grid is, linking power stations to consumers. Okay. So, well, recently in Nigeria, we've heard a lot of news. It has been a lot in the news that the national grid collapsed. Okay. And when that happens, I can tell you for free what happens when we feel it, when we are at home, how we at home feel it. Usually it means power outages would be longer than usual. That's number one. Number two, if the power gets restored, it would be, the bulbs would really be low, or, if it's a fan, the fan will not be spinning at the speed it's supposed to spin, or it might not even spin at all, depending on how low it is. Okay, so that's what usually happens when the national grid collapses. All right, so that's what happens when in a place like Nigeria. But yeah, I guess it probably happens, but not so often over there in the UK. Okay, so um, so I think we've talked about step-up transformers. Step-up transformers increase the potential difference from the power station to the transmission cables that go to our houses, and then well, they don't go to our houses directly. So let's just be factual. They go to the houses, but they must pass through another transformer, okay, that would switch, flip things around. And then they will decrease the current. And I think we said the reason why the current must be low or decreased. Number one, it's traveling over high tension cables, which are what, for long distances. And if current normally heats up cables normally. So if it's too high, if the current is high, the cables will be hot, and then that will be loss of energy by heat. Okay, and we want to cut down on loss of heat, the energy through heat, wastage of energy and all that. So that's why this arrangement is such a way that the potential difference is increased. Now, I want you to see something that is happening here. In your mind, in your mind's eye, or at the back of your mind, imagine that power is constant. Power is current times voltage, isn't it?
Yes.
So if power is constant, we are trying to say that either current will be high or voltage will be low, or voltage will be high and current will be low. So on the national grid end, you have step-up transformers that will ensure that the voltage is high. And that's the reason why high tension cables are called high tension cables. They can, they're dangerous. I mean, they are, I mean, fatal. An electric shock from them can be fatal. Then, but on the side of the homes, for us at home, we now have what we call step-down transformers, which will flip the equation. And in this case, the potential difference is now reduced to what our devices can carry that won't blow all our devices. And then the current can now be increased to the level that the devices can handle too. Okay, so I'm moving on because I've talked about that before, so I don't want to dwell on it too much. Okay, so we've talked about step-up transformer, reduce the energy losses due to heating. I've said that to calculate power loss, if there is a loss in power, of course, you use current times the resistance of the wire. Okay, that's how you calculate the power that's lost in the course of transmission. So we're not saying that it will eliminate it. Take note of the word reduce. It doesn't take it out of the equation totally. We can't, I mean, there's a law that says that energy, conservation of energy, the law of conservation of energy. Energy is neither created nor destroyed. So somewhere, somehow, somewhere, there will be a small loss of what? Energy. But we can manage it, we will just take it into consideration sometimes. So now I'm sure I don't know if you are with me and noticing why do we have I squared R? Now, do you have an idea why it's I squared R?
No.
Okay. Let me see. I don't want to edit this this PowerPoint, but I guess you have it on your site. So let me just edit it. Now, remember we said that power is equal to IV, isn't it?
Yes.
Now I want you to look at this thing very well. Remember, Ohm's law states that the summary of Ohm's law in an equation is that voltage, the potential difference across a circuit, is directly proportional to the current that passes through it. That's Ohm's law. I'm just paraphrasing Ohm's law. The constant there is the resistance in that wire of that material that Ohm's law is trying to cater for. So what that means is that V equals IR is also an equation. So remember, you already have I here. So this V itself is what? IR. So when you now have I times IR, can you see what's happening now? You now have I in two places, isn't it?
Yes.
So can you now see how the I squared R came about?
Yes, yes.
Okay. All right. I just thought to put that up. So I don't know if it would help you remember it, but yeah, that's how it happened. Okay, so moving on. Now what we've dealt with moving charges. Okay, so electricity, remember electricity is as a result of electrons, those free electrons in metals that we talked about earlier in chemistry, and now we're seeing them in physics. Those ones are moving, okay, as a result of potential difference applied across from one end to the other. So that potential difference makes the electrons to move in a particular direction. Okay, but it's also possible for us to have charges that are static. That means they're not moving, okay? And static charges, like I said, they may not, depending on how much they are, they may not be enough to give one a terrific electric shock if one touches it, but they are still significant in some aspects, okay? So we'll still have to take a look at them. All right, so yes, you have a question?
Triple means that I'm not supposed to do it. Like I don't have to look at this topic.
All right. Oh, okay. So we could skip this, right?
Yes, yes, yes.
Okay, all right. Okay, so all right, I'll look out for the ones that. Okay, particles and matter. Oh, this paper 3, right?
Then that means it's topic 3 of physics.
Oh, okay. All right, I just wanted to be sure. So that was not like, well, okay, so everything here is paper 1, but this is the third topic. Okay. All right, so I guess these diagrams look familiar. The first one reminds us of a solid because it's tightly packed and held in place by a crystal lattice. Liquids are not so tightly packed and they are freer to move. So that's why you see them like this. But you can still see those lines showing that there's some intermolecular forces of attraction between them. That's why they are still in liquid or fluid state, and they can take the shape of the container they're in. And then finally, gases, which are totally free to move because the intermolecular forces between them are so weak that the particles or the molecules of the gas can move freely, and thanks to their the level of kinetic energy in the gas. Okay, so these are the properties. You can just take a look at it to remind yourself. We said it, solids have a definite shape, have a definite volume, okay? So they don't need to take the shape of the container they are in. They already have their own shape. Particles are touching and they vibrate on their spot. They don't really move from where, they are positioned in the crystal lattice. The intermolecular forces are really strong. That's even what gives rise to them not being able to vibrate beyond their spot. They have low kinetic energy. Of course, they can't really move around. Remember, kinetic energy is as a result of movement. Okay. They do not compress. You cannot compress them because of that shape that they have. Okay. And then what do you have for the last thing? They are in organized rows and columns. That's the lattice structure we talked about. So on the other hand, you have liquids. Liquids don't have any definite shape. Of course, it doesn't now mean that they don't have a definite volume. They usually have a definite volume. So that's why we didn't say that they don't have a definite volume. They take the shape of the container, of the bottom of the container. I think that's better to be more specific. Okay, yes, we alluded to the fact that they have a definite volume. Particles are loosely arranged and slide over each other, 50% touching, okay? Medium intermolecular force, not so strong, but yeah. Medium kinetic energy, and they still do not compress. Well, maybe because of the fact that they still have a definite volume, right? So the definite volume will not permit them to compress. But here we have for gas, and you can see for gas, what do we have for gas? No definite shape. They take the shape of the container, okay? The whole container, not just the bottom anyway. No definite volume. They spread out as far away from each other as possible. Very low density. Okay, very, very low density. No thanks to the volume that is, just going really large. Particles bounce around and collide with each other randomly at high speed. Okay, that's what happens. That's peculiar to gases. And I mean, the intermolecular forces are very low. That's more reason why they can move really fast and really. Of course, that would make them have high kinetic energy, and they can be compressed. Yes, because their volume can, they don't have any definite volume, so you can push them into whatever volume you want them to occupy. Their volume increases with heat. Okay. Now, do you have an idea why that happened? Why would their volume increase with heat?
The volume. Because the movement increases.
Okay. So this is my question. If you increase their temperature, right?
Yes.
The volume of the gas will increase. So why do you think that happens?
Because the particles are moving more.
Okay, let me see. Okay. Do you know about the gas laws? You remember those gas laws, Boyle's law, Charles' law, Avogadro's law, all those laws, gas laws.
Yes. Yeah.
Oh, okay. So anyway, maybe we will come to those instances. But let's look at it this way, right? We put a gas in a container which has a piston on it. Okay, so a piston is like, that thing that looks like a pump, or like the trigger for TNT, a TNT explosion. You know how those triggers look like, that have a T on top, like something like a T on top. You push it down and then the explosion, the TNT goes off wherever it is. So I want you to just imagine that for a minute, right? That the gas is inside the container like that has that piston on top. Now, if you heat the gas, remember, gases, the molecules are already moving, have high kinetic energy. Then you now start heating it. What do you think will happen? The heat energy will get transferred to the gas molecules. And those gas molecules or particles will have higher kinetic energy. And remember, kinetic energy is what? Energy that enables them, that's as a result of what? Movement. Always remember that. Okay. Now remember that those particles, not as if those particles don't have they cannot do anything. If you keep on increasing the volume, what will happen? Because that piston, remember, it's a piston, it can move up and move down, right? Because the piston can move, the gases will start colliding with not just the body of the container, they will be colliding with the piston, the inside of the piston, okay? And because that part can move, because we are expecting the volume to actually increase, so it's designed to move. That collision with the inside of the piston will make it move upwards. Why? So that it can create more space. Because of that collision, the higher bombardment of the gas molecules with it will cause the piston to move up, to increase. And because it's moving up, what that is translated as a bigger volume. Did you understand my explanation back there?
Yes.
Okay, so remember, the logic is simple. Increase the heat, the gas molecules will receive that increase in heat as an increase in their kinetic energy, and as a result, the bombardment of the particles on the top of the cylinder where they are, and the piston will be more, and that will cause a movement of that piston in the upwards direction, which means that it will make it to increase in volume. Okay, so remember, higher heat, higher kinetic energy, more bombardment, therefore increase in volume. Okay, so that's just the simple logic about it. All right, so this is basic knowledge that you should know. When you heat a solid, it melts to give you a liquid. If you heat the liquid further, it vaporizes or boils at the boiling point to become a gas. Vice versa, it goes from gas back to liquid by condensation, and then from liquid, it goes back to solid by freezing, a process called freezing. Of course, there are exceptions to the rule. Sublimation can happen when a solid goes directly toward gas, and when the gas is going to turn back to solid, the opposite is called deposition. Okay, deposition. Can you tell me an example of a material or a compound? Yeah, a material that undergoes sublimation when you heat it.
When you heat it?
Yes.
Is sublimation or deposition?
Sublimation. Have you heard of manganese balls?
No.
Those small white balls. Maybe your mom might know what I'm talking about. Those small white balls that you usually put in between clothes to give them a nice scent. Or sometimes, okay, I'm sure you know this one. If you've gone to some restrooms, right, in hotels or in public places, those where you have where in the restroom, in the convenience, the sides where one can wee, you would see that they put some nice, colorful uh, balls or stuff like that, that, over time they emit some nice scents, stuff like that. Have you noticed them before?
Um, I think now that you describe it, yes, I think I have. Yeah.
Okay, okay. So those balls that you see there that have a nice scent, they are the primary elements in them is manganese. Okay, and that's the more reason why they're even used in that, for that application. They easily vaporize. They don't turn to liquid at all. If you had an opportunity to heat that thing, yeah, to heat it, it would immediately turn to gas. It won't, there's no liquid first, then gas. No, it turns to gas immediately. So they have a very good, that's a good property for them. Okay. Imagine a solid that can go to gas immediately. For that kind of application, somewhere that you need to be smelling nice all the time, right? If it gets hot, the heat will even help it to do what? Turn to a gas, and that will make the place smell nice the more. Okay. And typically, urine coming out from the body is usually warm. Okay. So that, I mean, that would equally make it even turn to gas the more. And of course, the gas that's coming out um, is pleasant to the smell. So yeah. Okay. So I'm moving on. Density is a measure of how much matter there is in a given volume, and density is given by mass per unit volume. Now, I don't know if you remember one of the properties of gas. We said here that it has very low density. The reason why is it that it has very low density? I'll use this equation now to explain it, because we have seen the equation. Because I didn't see it that time, so I don't want to start introducing something that we've not seen. So look at the formula for density. It's given by mass per unit volume. If we all agree that mass is usually fixed, okay? Mass is a fixed quantity because it's a measure of matter, isn't it?
Yes.
So my mass on Earth and my mass on the moon will still be the same thing. The only thing that may be different is my weight, because the acceleration due to gravity on the moon and the acceleration due to gravity on the Earth are different. Now, if we agree that mass is a fixed quantity, guess what? Volume is not fixed. How do I know? And now, when I say volume is not fixed, I'm talking about gases now. I've just explained to you now that when you heat up a gas, the bombardment can make it, heat up, collide with the walls of the container, and then the top of it, which will usually be a movable top, right, can now move up, and because it moves up, what will happen? The volume will increase. Now remember that mass is fixed. Now I want you to think mathematically. If the number on top, the numerator, is fixed, okay, so I want you to think about this very well. I'm about to ask a question now.
Yeah.
Let's imagine that my numerator is 1 1, oh, and my denominator, I start out my denominator with 2, okay? The volume is 2. At the time I heat up the gas, the more, the volume now goes to 3. Remember, the mass is still 1. So 1/2 and 1/3, which one is bigger?
1/2.
Thank you very much. 1/2 is bigger. So what is really happening is that as you are increasing your denominator, your density is reducing. Because look at it now. 1/2 is 0.5. 1/3 is 0.33. So it has already dropped. The density has dropped from 0.5, excuse me, to 0.33. Now, if the volume increases further, that's if you keep on heating that gas, the volume increases further to 4. 1/4 is 0.25. So can you see it's reducing? The density is reducing. And if it keeps on, if the volume keeps on increasing like that, to say 1/10, 1/10 is what? 0.1. So can you see why why it is said that gases have low density?
Yes.
So that's the reason why their masses are usually fixed, but because their volume can increase to whatever, whatever happens, whatever level they can be pushed to, then the density has no choice than to reduce. Okay, so I just felt I should just throw in that, because sometimes you ask yourself, why would they say a gas will have low density? What gives it that low density? That's the reason why. Okay, I'll skip this. I think it's something that you can read up. Okay, these are questions on density. I'm moving on. Okay. This is reference to internal energy. And yeah, we've somehow been talking about it, but I guess we now want to face it head on. So, first things first, all objects contain internal energy of some sort, okay? It's usually the sum of the kinetic energy of the particles and the potential energy of the particles. Remember what we said about kinetic versus potential energy. Potential energy is energy as a result of the position where it is. It's usually stationary, okay? The position. And while kinetic energy is energy that's a result of movement, shows up in movement, okay? Kinetic energy. You can even see it from, later on you get to see it from the formula for what? Potential energy, and the formula for what? Kinetic energy. Kinetic energy's formula has velocity in it. So, I mean, that should tell you something. If velocity, which is like the vector of speed, is in the formula, that means it has to do with movement. Whereas for potential energy, its own formula has to do with height, has height in it. Okay, so if height is in it, that has to do with position, where it is. Okay, so I'm moving on. When an object or a system is heated, its particles move more vigorously, and its what? Internal energy increases. I think I've explained this recently, so I don't want to spend too much time there. Sorry, let me move this guy around so it's not blocking our view. Okay, nice. Okay, so what's here? Let's look at specific latent heat of fusion and vaporization. Okay. Specific heat of fusion and vaporization. So Fusion has to do with solid becoming liquid, yeah. And then vaporization is when liquid becomes gas. So you can see it from um, the graph there. That's explaining those things. Okay. Do we have anything really much to say there? So the word specific is just the fact that it's related to 1 kilogram of that substance, because there could be latent heat, but it's not specific. So once we are talking about 1 kilogram of the substance, it now becomes specific. Okay, so I'll just move on. All right. So specific latent heat of fusion is given by ml. ml, that's the mass times the latent heat of fusion. This is an example. Okay. All right. That's just a quick reference. The temperature of a gas. Okay, now this is where we're now going to. We're looking at properties of a gas. The temperature of a gas is related to the average kinetic energy of the molecules. The average kinetic energy of the molecules. The higher the temperature, remember when we talked about heating a gas, the higher the temperature, the greater the average kinetic energy. The higher the temperature, the greater the average kinetic energy. And so the faster the average speed of the molecules. I think I've explained this, so I'm quickly glossing over it. Okay. How particles exert pressure? When the molecules collide with the wall of their container, they exert a force on the wall. Yes, I said that. The total force exerted by all the molecules inside the container on a unit area of the walls is the gas pressure. Okay? The gas pressure. And pressure is given by what? Force per unit area. Okay, so you know that. These are possible. This is a possible exam question. Let me see. Okay, so this is a graph that shows the variation of what? Atmospheric pressure with altitude. Altitude, of course, is the height above the earth. So the higher you go, they say, the higher you go, the cooler it becomes. But the pressure drops too. Can I explain this? Okay, so air molecules colliding with a surface create pressure through. At increasing altitude, distance between the molecules increases. So I think that's the reason why the atmospheric pressure decreases with increasing altitude. Yes, because the distance between the molecules increases. So the number of collisions with a surface will also do what? Decrease. And then that's what will also lead to a decrease in atmospheric pressure. Okay, did you get that?
Yes.
Okay, all right. I don't know why this was. Did I cancel it? Oh, hold on. I'm sorry. Sorry, my bad. I should have, I forgot that triple thing. I'm so sorry. Okay, so should I also leave this since it has to do? Okay, now let's discuss it since it doesn't have that triple thing on it. Okay. So pressure law is says that if you change the temperature of a gas that's held at constant volume, the pressure will change. It will also change in pressure. Increase in temperature increases the pressure. Decrease in temperature decreases the pressure. That's the pressure law. PV equals a constant.
Yeah.
Okay. All right. Okay.
They are not taking your medicine.
All right. So we're moving on to radioactivity. Okay. So I'm sure these ideas are familiar, these concepts are familiar to you. Atomic number and mass number. The number of protons, the number of electrons, which is also equal to the number of electrons, is atomic number. Then atomic mass, or the mass number, is the number of protons plus what? The number of neutrons in the nucleus. Okay? So that's it. So if you saw this diagram, what would you say is going on here?
Increase in neutrons.
Okay. That's one way to say it. How else do you want to explain it? There's another concept that is there.
The adding one proton.
Okay, yeah. Okay. So this is the concept. Yes, you said you remember the concept of isotopes, right? Do you remember?
Yes.
Okay. So that's it. These are isotopes of hydrogen. Okay. So it's isotopy basically. That's playing out here. So anyways, that's the concept. So this basically happens more with when we're discussing radioactivity. Okay. So yeah, remember the definition of isotopes. Same elements, different number of neutrons. They have the same proton number, of course, the same atomic number. That's the reason why they are the same element. It's usually the element, the atomic number, that tells us the elements that we're dealing with, usually. Ionization is when radiation from a radioactive substance knocks electrons out of atoms, okay? The atoms then become charged. So remember the concept. When you knock off electrons out of an atom, it will be positively charged. And if electrons get transferred, vice versa, it will be negatively charged. It says this process may be harmful to living cells, hence why the precautions that are taken during radioactive experiments, wearing of clothes that are lined with lead and all that, necessary to avoid exposure to radiation. Okay, so what's radioactive decay? It's simply the process where radioactive atoms may become unstable by having too few or too many neutrons, they become unstable. Okay, and when they become unstable, the nucleus decays and emits radiation. And then they can now, until they become more stable. Okay, so that's the whole idea. When they're unstable, they emit radiation. Now, there are different types of radiation that could be emitted. So that's what would tell us which type of what's going on when it comes to decay. Okay, so well, these are some things that I think these are indirect references to experiments for radiation. So what's the count rate? The activity that is captured by a gigamolar tube is always much less than the activity of the source. The activity is the rate at which a source of unstable nuclei decays. It's measured in decays per second. Okay. But they didn't really give us a definition for the count rate. Anyway. I think if we know the activity, anyway, let's look out for it. I think they would make a reference to the count rate. Okay, so this is supposed to be a table. I don't know if they completed it anywhere here. Okay, anyway. All right, so there you go. You have an unstable nucleus that has a lot of neutrons, okay? It has neutrons and protons. So how is alpha radiation created? Alpha radiation is created when alpha particles get radiated out of the new nucleus. Okay, so whatever it is, we're saying that the alpha particle will be made up of ions that of let's say nuclei that have mass number of 4 and atomic number of 2. What that means is that the emission will be of helium particles, because helium particles have what? 4 and 2. If you remember, let me take you back to that first diagram. Look at it. 4 here at the mass number, that's sum of protons and neutrons, and 2 is the number of protons. So going back, okay, so it's a helium, okay? Alpha radiation is the nucleus of a helium, traveling at an extremely high speed. Okay, so what's a beta, what forms the beta radiation? Simple, it's an electron, high energy electron, fast moving high energy electron. It's a beta particle. So electrons, you can think of them that their mass number is 0, while their, what you would call their atomic number is -1, something like that, sure. So they have something unique about them. But if we see any equation that has to do with balancing, I think I'll spend more time on that. Okay, then the last one is gamma radiation. Okay, so it says after an alpha or beta decay happens, surplus energy is sometimes emitted. Okay, and the atom itself is not changed. So gamma radiation is part of the EM, electromagnetic spectrum, a wave with a very high frequency and very short wavelength. Okay. All right. So these are the safety precautions for a radioactivity demo or experiment. I want you to take a look at them. Is there anyone that may be confusing? I think all of them are quite straightforward, right?
Yes. Yes.
Okay. 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 Okay, so I'm not too sure if you are supposed to memorize all this, but anyway, yes, they are good to different models of atoms. That's people that who are trying to explain how atomic structure, Thomson's model, and so on and so forth. So these are usually, I think these are usually in reference to experiments. Let me go to the ones that are usually more questions. So I want you to take a look at this. Can you see that this is an example of alpha radiation?
Yes.
Do you understand why it's alpha radiation? If I was to ask you, what would make this to be alpha radiation? What is it that makes it alpha radiation? What would you say?
Alpha is the one that
Yeah, go ahead, I'm listening.
Yeah, alpha is the one that has the positive charge, right?
Well, if we look at it that way, okay. Maybe we should look at it this way, right? Yes, it's positively charged, and the reason is because it's the nuclei of a helium atom, right? The nuclei of a helium atom has 2 neutrons and 2 protons, okay?
Yeah.
So since it's the nuclei, what does that tell you? It means that the electrons that the electrons on the outside are no more in the picture, right?
Yes.
So that should now make it positively charged. Yes, I agree with you. Well, yeah, so the important thing is this, right? Just understand that it's the nuclei of a helium atom whose mass number is 4 and what atomic number is what 2. So that's this one. This is where it says here. This is our radioactive element. You need to remember the mass, atomic number, and the symbol. Okay. So having the alpha symbol there, it's not really, may not look like that. Just understand that the elements there that alpha is representing is a capital H, small letter E, helium. Okay. All right. So what I just needed to see is that these numbers always add up. The mass number for the guy that decayed in this case is 241. The atomic number, excuse me. Excuse me. All right, so the atomic number for the one that decayed is 95. Can you see that when it decays, when the alpha radiation happens, the atomic number reduces to 93 so that it can make space for the radiation that came out, which is 2, so that its atomic number is 2. While the mass number also reduced from 241 to 237, so that it will make space for the 4, which is the atomic mass or the mass number for the helium atom. So those things must add up. When it comes to knowing what is what, that's how you know what's happening. Okay, so let me see if I can just really arrange these guys. These things are really, 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 really scattered. Okay. Okay. So okay. Okay, can you still see my screen?
Yes.
I'm not too sure. These things are really looking scattered, right? And I think they were set in a part of the document that I don't have access to right now. So let's just manage it. Let's see if we can deal with it. You remember when I told you about beta particles, right? That beta particles are, yes, or beta radiation, that it's electrons, that the mass number is 0 and the atomic number is -1. So let's look at how that plays out in balancing this equation. Now, if you add 7 and -1, you actually get 6, isn't it?
Yes.
And if you add 14 and 0, you will get back 14, isn't it?
Yes.
So do you see that it's everything balances well?
Yes, yes.
Okay, I just wanted to bring that to your attention. Okay. Let me turn this, flip this guy the other way around. Okay. Okay. So this is an example of a question. This is how the question typically looks. An atom of the isotope radon-222 emits an alpha particle and decays into an atom of polonium. An alpha particle is the same as a helium nucleus. Just a reminder. The symbol below represents an alpha particle too. How many protons and how many neutrons are there in an alpha particles? I mean, it's like a giveaway, 2 and 2. Number of protons is 2, number of neutrons is 2. Let me remove this so that I can see the question. Yeah. The next question says, the decay of radon-222 can be represented by the equation below. So that's the radon-222. It says complete the equation by writing the correct number in each of the two boxes. Of course, by the time you subtract 4 from 222, you have 218. And by the time you subtract 2 from 86, you have what? 84. Okay. So did you get that?
Okay. No, can you say again, please?
All right, let me say it again. Can you see the mass number for radon on the left-hand side? I'm talking about, this is the one I'm talking about.
Yes, yes.
Second question. Okay. So the mass number is 222, while the atomic number is 86. So because you know this is an emission, so something is going out. And you already know that the alpha particle has what? 4 and 2. 4 on top, 2 below. So I'll subtract 4 from 222 to give me 218 at the top. And subtract 2 from the atomic number to give me 84 below. Did you get that?
Yes, yes.
Okay, that was what I said back then. All right. Okay, so I hope this will not trip us up, but half-life has to do with a different, slightly different concept from decay. Okay, decay is what we talked about that produces irradiation on stable nuclei, usually one nuclei. We're talking about one nuclei. Whereas half-life is the time it takes for the number of nuclei in a radioactive material to be half of its original number. Okay, so so this is like a graph. I think just keeping them. Okay, so this idea of half-life, right? We have to okay. Trying to arrange this down. Okay, can you still see my screen?
Yes.
All right. Okay. So this is a word problem. Let's see how this should play out. A radioactive isotope of lead has a half-life of 10.6 hours. A small sample of lead containing containing this isotope has a count rate of 8,000 counts per minute. Okay, so it says, how long will it take before the count rate is 1,000 counts per minute? Okay. So 8,000 counts per minute. So this okay, I think I understand what's happening now. I was wondering why there were 3 arrows. I think I get it now. I get it now. But I now don't know where to move this thing so that it will make sense to our working here. I'll move it up like this. Okay, let me just see. So ideally, right, this should be, it should be something like this. But I'm having 1,000 on top. So this is what happens. 8,000, by the time 8,000 is halved, it will become 4,000. That is the first half-life. When 4,000 is halved, it will become 2,000. That's the second half-life. And when 2,000 is halved, it will become 1,000. That's the third half-life. So that's how we arrived at these 3 half-lives. And if 1 half-life is 10.6 hours, then 3 half-lives will be 3 times 10.6 hours. Okay, 10.6 hours, which will give us 31.8 hours. So that's how this was arrived at. That's how it was arrived at. So actually, in real sense, this 1,000 should be at the bottom. Let me see if I can arrange it that way. It does that. It won't just look like it anymore. That's just issue. 1,000. Okay, so 800 became 400. 400 became 2,000. 2,000 became 1,000. So I think it's better this way. Yes, it makes more sense like this. Did you get the explanation back here? Hello, no, are you there?
Yes, I understand the definition.
Okay. Okay. Radiation seems to be a lot, but yeah, I guess. Okay, so these are concepts, basic concepts of radiation, right?
Yes.
Radiation versus contamination. I think I saw one of those questions that we've done before had a reference to this. I remember. It says when an object is exposed to ionizing radiation but does not become radioactive, then it's irradiated. Okay, so that's the difference between it and contamination. Contamination is when a radioactive substance is present on a surface, on a substance or within solids, including the human body, where their presence is unintended. So that's wrong. All right, so that's the difference between contamination and irradiation. These are examples of background radiation. So they are not exactly actively, radiating, but they could be still dangerous if not checked. All right, so applications of radiation, right? Let me see, these applications. Okay, smoke alarms, right? To detect smoke in a building, and I think equally in cameras. So how do they work? Smoke alarms usually contain a source of alpha particles. There is an electrical circuit with a gap between two charged plates. Air in the gap is constantly ionized, therefore the constant electric current. When smoke gets in, the alpha particles the alpha particles are absorbed and stops the current and stops the current and stops. Then the current drops and then an alarm sound. So that's the basic way and a smoke alarm works. Further uses of radiation are, number one, irradiating food. Okay, remember, irradiation does not make a substance to become radioactive. That means it will start emitting rays, which are harmful. It simply, helps. So gamma rays can kill bacteria
No, that's so expensive to see.
So if it can kill those bacteria, then that means it can be used to preserve food, stay safer and longer. It doesn't make the food radioactive, so that's fine. Foods like fruit, cereals, and shellfish are irradiated. Okay. Of course, for cancer diagnosis, even in X-rays, okay, to find broken bones or, find stuff in the body, stuff like that. Okay, so gamma rays are used for diagnosis. And we also know about radiation, use of infrared. Okay, so infrared, yeah, okay. Infrared is a different type of radiation though, but that's what you find used in security cameras and all that. Okay, so sterilization of equipment, of course, can kill bacteria, can kill other microorganisms on surgical equipment that need to be sterilized before use. Heat is usually used, but cannot be used on some things like plastics. Yeah, we definitely melt it. So they are irradiated with gamma rays instead. Okay. So take a look at this. This is more like a summary of nuclear power, right? And
Yes.
some things that apply to it. But I'm not too sure you really need all this. But I think you can just take note of some concepts, like where it comes to disposal methods, right?
Oh, okay. Yes.
Disposal methods and which ones are the best. Yes, disposal methods. Firing them into space, risk of it falling back is there. So that's not the best. Dumping in barrels at sea, barrels can corrode, it can enter the food chain. Storage underground needs a geologically stable site, low earthquake risk. So I think that storage underground is usually a more, well, technically safer method, right? So yeah, you can say that. Then another thing that you need to take note of is the impact of nuclear power on global warming. And that's the reason why some countries that have embraced use of nuclear power to generate electricity are, somewhat green in their approach to electricity generation. Okay, so those are the advantages. But of course, there are disadvantages. Making of fuel rods require energy. So that same energy we're trying to avoid, that CO2 will be released. You cannot totally avoid it. And then waste has to be stored for tens of thousands of years without leaks. And people perceive it as unsafe. Okay. So I think there was an accident that happened somewhere, either in Ukraine or so, either the Soviet Union, somewhere in the Soviet Union. So that's the reference to that Chernobyl accident. Of course, nobody needs to remind us of what happened when the atomic bomb was detonated over Japan by the US. Okay, so the other ones are reference to triple only. So I think we can safely skip them. And well, these are parts of a nuclear reactor, which I'm not sure I've seen any question that referred to this. So probably it's under triple only too. Okay. So is there any part of this that you want us to revisit?
Beginning.
Yeah,
The energy.
The energy part.
Yes, please.
Okay. Okay, I think this is it. Okay. So energy start with forms of energy, right? How many
Yes.
forms of energy can you name? So how many forms of energy immediately come to mind?
5.
Okay, let's have them.
Sound, kinetic, gravitation, magnetic,
Okay.
light, yeah, that's and chemical. Yeah, that's all I remember.
Okay, chemical. Did you mention electrical?
No, I don't think I did. Okay, yeah, electrical.
Okay, so electrical, yes. Okay, so these are the ones that among the ones that you mentioned. Thermal, which is heat. Light, I think you mentioned light. Sound, elastic. This is what you find in springs. Okay.
Yeah.
So of course you can see their application in areas like shock absorbers of cars. Okay, shock absorbers and all that. Gravitational, I think you mentioned kinetic, electrical, chemical, and nuclear energy. Okay. All right, so these are examples of where you can find those energies happening in a spring, elastic band, bouncy ball. That's where you can find elastic energy. Gravitational energy, see the applications. Book on the shelf, aeroplane, anything high up automatically has gravitational energy. In fact, let me just say it here. There's a big world of similarity, if not even exactness, between gravitational energy and potential energy. You see this word, anything high up, that suggests to you that there's a height somewhere. It suggests to you that there's a height somewhere. And what that further suggests is that it has that energy it has there. It's as a result of that height. And I told you that potential energy has to do with position. Position has to also do with height. So, one may be thinking, a book on a shelf, does it really have energy? But I can give you a very good a scenario. If you leave a glass cup on somewhere close on the floor, and maybe somebody mistakenly trips it, the likelihood of it breaking in pieces is slim, isn't it?
Yes.
Not as high as if you now raise the glass cup and put it on top of a table and it mistakenly slips from that table. So what made it so sure that once that glass cup hits the floor, because it was on a table that has a height, it will definitely break? This is what happened to it. When it was on that table, it had a potential energy. But when it fell down from the table, that potential energy started getting converted to what? Kinetic energy. But it didn't all finish. By the time it hit the floor, some of the energy that was left would be converted to the point where it would, break the glass in pieces and make the parts, the pieces to go in different directions. So that is also potential energy in a way. All right, so yeah, like we said, kinetic energy is energy of things that are moving, electrical, anything that uses electricity, chemical, batteries, food, matchstick, candle, nuclear energy, nuclear bomb, nuclear power station, etc., etc. Okay. All right. So one thing to note is that any wasted energy is transferred to the surroundings, usually transferred to the surroundings as heat. Okay. It says energy can neither, this is the law of conservation of energy. Energy can neither be created nor destroyed. It can only be transferred or changed from one form to the other. This is a good example. A ball gains gravitational potential energy. So you remember I said these two are the same. So this is a confirmation of it. A ball gains gravitational potential energy when it is lifted above the ground. It is turned into kinetic energy when it is dropped, and sound energy, okay, when you hear the ball hitting the floor, that's sound energy. And then thermal energy, heat, when it hits the ground. To some extent, the ball warms up. It may not be too noticeable, but the ball warms up, okay? All right, so these are some energy transfers that we can consider. A speaker is simply changing electrical energy to what? Sound energy. Okay, that's what a speaker is doing. Electrical energy to sound energy. Wind turbines change kinetic energy of the turbines, the blades that are moving, being moved by the wind, to electrical energy. So the idea for energy conversion is to be very calculative about where the energy starts, where the process starts, and where it ends. So someone looking at these wind turbines, look very well. What's the aim? The wind turbines will end up creating electricity. So that's the destination. But where is the source? Where does it start from? It's the wind that has to blow it first. So that wind blows on the turbines. Then turbines, there's a what they call a dynamo or something in the mechanism of the turbine. And that dynamo has some wires connected to it. And the electricity now flows through those wires to wherever the destination is. So that's why it's kinetic energy moving to electrical energy. Now, this is another demonstration, something that's very practical. Gravitational potential energy is converted to electrical energy. Water that is dropping from a height can spin a turbine. Those turbines are inside the dam, okay? So we don't see it here, but those turbines are inside the dam. So that water is coming with great force. And because it's coming with great force, it's the same way the wind spins those wind turbines. Air in motion has energy. Water that is falling from a height has even more energy than that, okay? That's what gets converted to electrical energy. For a television, there are a couple of things that are happening. It's not just one line conversion. It's electrical that goes in to the television set, but things come out from the television set. Number one, light. Then you also hear sound from the signals of the station, and then, of course, heat. You touch the TV after a while, you notice that it's warm. Okay, that's wasted energy. Okay, not really useful to us. Okay, for a radio, it's just sound. But what goes in? Electrical, that's the source. Destination, sound. And then, of course, wasted energy again, which is heat. Okay, so in all the devices and all the energy conversions we have seen so far, the efficiency of those processes is to ensure that the heat that comes out is the lowest it can be. So that's where efficiency comes in. Ideally, because consumers or businesses want appliances that are more efficient, whether it's in terms of consuming the fuel or it's in terms of heat loss. Efficiency is key. Why? Because it saves money and helps them to use that money to produce more product for the same amount of money that was saved. Environmentally, less fossil fuels are burned, so less carbon dioxide is released into the atmosphere. These are critical terms that you may need to use in your explanation. Okay. Of course, okay, this is a formula for efficiency. Useful power output over total power output times 100%, times 100 over 1. Okay. Now, this is the main thing. Because useful energy output is usually smaller than the energy output. Why? Because of the loss of small energy. That loss will, ideally, it would have been a good thing if all the energy you sent in came out. But because there will always be some level of friction or material resistance and all that, you will never get all the energy that was pushed in. Something must be lost. So because that loss is there, the numerator of efficiency will always be less than the denominator. And that's why you would have a decimal. Okay, if you're using your calculator, you always have a decimal. Then you can now multiply that decimal by 100 because it's 100 over 1. Okay, so that's what you need to take note of there. And so this is an example of questions that can come on efficiency. This first one, right? This first one, I know we probably skipped it, but since we are revisiting it, I think we have some time on our hands, so we're not rushing it. It says the student finds some information about energy saving light bulbs. 30-watt bulb uses 600 joules of electrical energy in a certain period of time. In that time, it produces 450 joules of light energy. The rest of the energy is wasted. Question, calculate the energy wasted by the light bulb in this period of time. Remember, it produces 450 joules of light energy. Meanwhile, the electrical energy that went into it was 600 joules. So that means there was a loss of what? 150 joules. Question, it says, what happens, the next question says, what happens to the energy wasted by the bulb? We already concluded. It's transferred to the surroundings in the form of heat. The next question, it says, calculate the efficiency of this light bulb. I think this should actually be 450 over 600 times 100 over 1. Okay, can we confirm that calculation? 450 divided by 60. 450 divided by 600, please. Can you use your calculator and help us confirm it?
Yeah, 0.75.
Okay. Let me just correct it. All right, so it's 0.75. Don't forget to multiply by 100. That's where you get 75%. Okay, here we go. Question, I think I answered this question, but let's look at it again. It says, use the words from the box to complete each sentence. In the batteries, chemical energy is transferred to electrical energy in the wires. And this electrical energy in the wires, the fan has kinetic energy as it does what? It rotates. So it's just that we don't want to get too technical, but you know that in the mechanism of a fan, there are magnets somewhere. There's a coil, there are magnets. So there are even some energy conversions that we don't, because of complexity, we don't want to go into them. So that's why we just say, oh, a chemical, and in this case, it's a fan that uses batteries. What if it's a fan that cannot use batteries? That means it's going to be electrical straight. Electrical to what? Kinetic energy, period. Because of that movement of the fan blades. Okay. So very critical to know what's happening where. Okay. Okay, so if I were to ask you, right, in a car, in an automobile that is moving, what's the energy conversion that you perceive is going on there? Can you guess? Can you just tell me? Carefully analyze it in an automobile that's moving. What are the energy conversions that are happening?
Kinetic.
Remember, when I was explaining energy conversions, I started with the source. So ask yourself the question, where is the source? Don't just give me the destination. Tell me the source. And where did that source move from what to what? That's what I want to hear. Now, let me give you some clues. I'm just giving you clues now. Can you think of the fact that a car, that these days now, we have cars that are powered by batteries, like Tesla and the rest, electrical vehicles, that's EVs. But let's leave those ones aside. Let's look at cars that are powered by gasoline or petrol or diesel. Okay. What is the energy conversion that is happening in those cars? Remember, start with the source.
It's chemical.
Yes, chemical is the first, because chemical is stored in the petrol that's in the tank. So what happens next?
Electrical.
Okay. So let me see if I can step in at that point, right? So I'm going to try and make it, take out some of the processes as simple as possible, right? You turn on the ignition of a car. What really happens is that you cause a spark in the engine chamber. That spark causes fuel to explode inside the engine chamber, and that makes those pistons to go up and down, right? So think about it this way. There's chemical energy stored in the petrol that's in the tank. When the car is stationary, nothing is happening. Turning the ignition on causes that spark in the engine chamber of the car. And that is now a form of what? Heat energy. That heat energy and the explosion makes the pistons in the engine to move. That is kinetic energy, which is transferred to the tires. That's still kinetic energy. So can you see the energy conversions, how I went from one to the other?
Yes.
Okay. Now, let's do one more. before we move on. Can you think of what is the energy conversion in a generator? You know, like the generator that you have in a house that would give you electricity when there is no light. What's the energy conversion there?
Is there thermal?
Okay. There's a form of thermal, but that's not the starting point. Again, right? The starting point is chemical because those generators have a tank and you have either petrol or diesel in them, right?
Yes.
You start them and they start moving. Okay. So that means there's chemical to kinetic at a point, and then kinetic will now help to generate electricity. So that's electrical energy. So anyway, that's the whole idea. In an electrical ion, it's simply electrical energy to heat energy. Okay, electrical energy to heat energy. That's what's happening in an electric ion. Okay. Okay, I'm just looking at this concept. I'm not sure but yeah. Okay, I think I just subtly made a reference to this, that work done is equal to kinetic energy, gravitational potential energy, or elastic potential energy. All these have formulas. So the question usually gives you the formula. So I don't really want to go into them. When an object is moved, there must be work done to move this object. A force must be applied over a certain distance. That's the reason why the formula for work done, is force times distance. Force times distance. That's the reason why. So that's why you see the F times S. Okay. So this is an example. Force times distance. Right. Now let me ask, can you guess something? Why do you think we didn't use 1.1 in this question? Instead, we used 2.6.
Because that's the distance.
That's the distance that was covered by the what? The force. Okay. So yes, that's the distance. This one is same thing. Calculate the work done by a worker to push the crate 28 meters. Okay. Show clearly how you work your answer. Of course, again, you applied a force of 60 newtons in forward direction, and the crate was moved over a distance of 28 meters. So that's 60 times 28, 1,680. That's all. And of course, the unit, you know by now, the unit is what? Is joules, please. Unit for work done is joules. Okay, so this is what I was telling you back then. I think you haven't seen it said that kinetic energy has velocity as part of its formula. Hence, why it's always all about movement. It's always all about movement. Okay. Velocity squared, half times mass times velocity squared. Okay, so these are examples for kinetic energy. A car traveling at a speed of 20 meters per second, when the driver applies the brakes, the car decelerates at a constant rate and stops. The mass of the car and the driver is 1,600 kg. Calculate the kinetic energy of the car and the driver before the brakes were applied. So that's going to be half times mass times velocity squared. So I think they meant to say 20 raised to power 2, and it's now looking like 202. So I need to correct it. I'm going to correct it by making this guy a subscript. Let me see if I can highlight it alone. No, I cannot. So I have to delete that too and look for subscript or superscript. Sorry. Let me quickly just correct it. Superscript. Where does that play out again? Okay. I know superscript is somewhere. Okay, I think I know where. Under insert, and where you have symbol, right? Yeah. And have, sorry, let me just quickly tidy this guy up. Where is there? Okay, that's it. Right. Yes. Okay, so yes, so that's 20 squared. By the time you calculate this, this is what you get. It's correct now. Okay. These are more exam questions on velocity. Okay. No, not velocity. Kinetic energy. Okay. Okay. So let me see. I think the energy part, you have a better appreciation of it, right? Do you?
Yes.
Okay. Okay. So it's only physics you have tomorrow, right?
Yes.
Okay, so would you be able to still go through some of it tonight before you go to bed?
Yes, sir.
Okay. All right. So I think we should just call it a night or a day, yeah. And okay. All right, so just enjoy the rest of your evening, and I believe everything will go well tomorrow, and It will be good to have some time to rest before we continue.
Thank you.
All right. Okay, so I'll check on you probably on WhatsApp, you know how the exam went. Okay, so do have a good night rest.
Thank you. You too. Bye.
All right, goodbye.